The problem which we have considered over here is the multi-item single-level capacitated dynamic lot sizing problem. It consists of scheduling a variety of 10 different items over the planning horizon of t time periods. The main objective when considering the multi-item single-level lot sizing problem is to minimize the combined inventory holding cost, setup cost over the planning horizon subject to the capacity constraints in each planning period. Now, we have considered two different heuristics for our purpose. The first heuristic is the extended Dixon-Silver heuristic, and the second heuristic is the extended Eisenhut heuristic. Now, these heuristic procedures have been coded using Python, and a common data source has been provided to both the heuristics. The outputs obtained through both the heuristics have been analyzed to show the results. After that, uh, I'll walk you through the code. Now, the first heuristic through which is considered over here is the extended Dixon-Silver heuristic. The original multi-item problem with constant capacity is considered to be NP-hard. Hence, a simple heuristic has been developed over here. The first, what we do is we input the data from the CSV file. The input data consists of holding and setup cost, maximum lot size, and production rates. We also input the forecasted demand. Then we create a pandas data frame from the forecasted demand. First, we initialize the time period as 1, and then we initialize the remaining inventory as the difference between the initial inventory and the safety stock. Now, this initialization is then used to calculate the equivalent demand matrix. This equivalent demand matrix has been used later. Now, next, what we do is we check the feasibility of the problem. In that, we check the sum of total demand for all the items should be less than the sum of total capacity for all the items. If the feasibility condition is not satisfied, then we show that the problem is infeasible. That is, all the demands cannot be met with the available capacity. Now, the next step to be considered over here is converting the multi-setup problem into a single setup problem. Uh, so for that, we first calculate the maximum demand, and then we split the n number of items into n dash number of items. Here, an item I is split into ni plus 1 items if the maximum demand for that item is greater than the maximum lot size. So n dash will always be greater than or equal to 1. This maximum lot size consideration is the main characteristic of this paper or this heuristic. After taking that into consideration, our new matrix becomes an n dash cross h matrix. Uh, the dimension is n dash cross h. After that, we initialize the setup cost, holding cost, and the production rate for all the n dash number of items. Then we start the time period at 1. Then we initialize the value of lot size by equating them to the demand. After that, we set the value of the time supply to 1. Here, the time supply denotes the integer number of time periods that this lot will exactly satisfy. After that, we calculate the remaining capacity and we initialize the updated inventory. Now, next, we want to calculate the value of cost coefficients. For that, first we must calculate the value of X scan, which is the difference of equivalent demand and the remaining inventory. Now, to calculate the cost coefficient, which is UI, we first check three conditions such that Ti dash should be less than Tc, the value of Xcan should be greater than 0, and the difference between the remaining capacity and Xcan should be greater than 0. So the value of cost coefficient is calculated, and then we check for all the positive cost coefficients. After checking the positive cost coefficients, we increment the value of the lot size, the inventories, and the remaining lot sizes by the value of xcan for the period r, and decrement the value of the same values for another time period, which is r plus ti, by the value of xcan. Then we update the value of ti by 1. Now we check if we have covered all the time periods. If not, we repeat the steps. Now, next, what we do is we calculate the value of Q, which is the amount of production still needed in the current period. The formula is mentioned for Q over here. After that, we calculate another coefficient, which is delta I, and we select the minimum of the deltas uh, instead of the maximum which was chosen for all the UI coefficients. After that, we calculate the value of W, which is Ki into Xcan. We check if W is less than Q. If that is satisfied, then we update the value of lot size, inventory, and the remaining lot sizes. And if that is not the case, then what we do is we calculate another value of IQ, which is Q by K, and update all the values. We repeat the procedures until all the time periods are covered. If all the time periods are covered, then we say that the heuristic is completed, and then we calculate the sum of lot size for all the n dash cross h items and convert them to n cross n h items, which is the original dimension of our data set. After that, we calculate the inventory setup and holding cost. Now, we run this Python code, and the output which is generated is uh, the total cost is shown, the inventory carrying cost is shown, and the is shown. The values of the lot size, that is the production plan, is shown for each and every time period, which is saved in the CSV file. This CSV file, there are two different CSV files. First is the one shown over here, which contains the lot sizes, and the second file is generated, which shows the inventories. So two different production plans are generated, and the costs are computed. Now we move to the second heuristic, which is the extended Eisenhower heuristic. For the second heuristic, we generate the equivalent demand matrix first. Now, the main advantage of this heuristic is that it removes the infeasibilities which were present in the original Eisenhower heuristic using the feedback mechanism. Now, uh, to check for the infeasibilities, first we check if the sum of demand is less than the sum of capacities, and then we calculate the value of the order of two period. Then we compute the value of inventories, and after that, we compute the values of the cost coefficients. Now we check for the positive cost coefficients, and if there are none, we move to the feedback mechanism. But if some positive values are present, then we select the maximum of cost coefficients, and we increment the value of the lot sizes by the demands. For increment the lot sizes of the previous period by the demands, and decrement the remaining capacity and the demands by demand. We repeat this procedure for all the positive cost coefficients. Now, for the negative cost coefficients, the infeasibility, the amount of infeasibility is calculated. We initialize the value of A as 1, and our main objective over here is to remove the infeasibilities. We do that by checking the minimum of the holding cost. If the minimum holding cost is present, then we move that many items to the previous time periods. Uh, After that, we decide the amount which has to be incremented and decremented from those respective time periods. Then we calculate again the infeasibility and repeat this procedure until all the infeasibilities are removed. After all the infeasibilities are removed, we calculate the final inventory. And after calculating the final inventory, we calculate the inventory cost, the setup cost, and the total cost. Now, after running this code, the output which is generated is again in form of total cost, inventory cost, and setup cost. And the output files are generated in a CSV, which gives us the production plan and also uh, the inventories. Another thing which we do is we generate a another thing which we do is we generate an animation to show the data. Now, this animation is helpful to visualize the data in an effective manner. As we can see over here, the costs are shown on the y-axis and different data points are developed. This animation shows the various two different data sets and the values obtained from two different heuristics. It is observed here that the total cost for the Eisenhower heuristic is comparatively more than the Dixon-Silver heuristic, and hence for our data set, it can be interpreted that the Dixon-Silver heuristic provides better solutions. Now, these animations are saved uh, in as a plot.